All right, we're going to consider the center of a group, which is often denoted by this Z of G. And we're going to show that for any group, the center of the group is a subgroup, meaning the center of the group is also a group. So let's take a look. So remember what a group is. A group, we have some sort of set and an operation. So here we have the operation star, and we're going to use that operation when we talk about the center. So the group has all these properties, and the center is also going to have those properties. We're going to take the center as some set and an operation. That's a group has to be a set and an operation. The center, we're going to have the same operation. So the center's operation is going to be also the operation that came from the group. And then the set is going to be some subset of the group. So G is all the elements in G, but we're going to take some elements, let's call them Z, some element Z in G such that Zx equals Xz for all X in the group. So there's certain elements in G. Some subset of G has this property such that if I take any element of the group, I can multiply on the left or the right, and I'm going to get the same answer back. Our operation star from the original group is going to give us back the same answer. Okay. Now the first question, we're getting used to the center here, is to ask, all right, is there any element that obeys this, right? We're just saying let G be any group. So we need to make sure that, hey, if G could be any group, there's tons of examples of groups out there. Am I guaranteed that there's at least one special element in the center of a group? And whenever we think about a special element of a group, a good place to start is often the identity. So if we consider that every group has to have an identity, then let's see if the identity would obey this property. Well, certainly the identity obeys this property for any element because that's part of the definition of the identity. So we know at very least that this center, this thing we're calling the center, has at least one element because it at least has the identity element, which is very useful because what we want to use here is this lemma. So instead of checking all four properties of the group for the center, we can just use this lemma 2.3.1, which says a non-empty set, which we know we're non-empty, in a group is a subgroup if and only if two things. So what are those two things? We have given an element A, then the inverse is also part of our subset, and we also have it's closed with respect to the operation of G. So all we need to do to finish this problem to show that the center is a subgroup of G is to check these two conditions. So let's go ahead and start with closed with respect to the operation of G. All right, how do we check the closed condition here? So we're going to let any two elements belong to the center. So if the center has more than one element, we're saying, hey, take one element X, take one element Y, and we want to show that the product of these two elements also belongs to the center. Well, what does it mean for the product to belong to the center? Well, this is an element of the group G, right? We know G is closed, so we want this element to be part of the center, which means that for any, here we're using lowercase g in G, for any G in G, we must have this equation must hold. xyg has to equal gxy, because then our element follows the requirements to be in the center. Now, because we have x and y themselves are in the center, that's where we get these two equations. By definition, if x and y are in the center, we have these two equations hold. xg equals gx and yg equals gy. And now, this is what we want to show is this right here, is that xyg equals gxy. That means the element of G, which is called xy, belongs to the center of the group. And so what we're going to do here is we're just going to manipulate the left-hand side until it looks like the right-hand side. So if we start with xyg, what do we know we're allowed to do? Well, in our first step, think about why we're allowed to change our parentheses here. Here we have x, y, and g are all elements of the group. We started with the group G. We're focusing on some special elements, but everything belongs to G. And so this first equation comes from the property of groups, which is associativity. We can apply our parentheses in how we want. And then now what we can do is we can apply our definitions how we like, and we can change the yg to gy, again use associativity, and then again use our definitions above, and that will show exactly what we wanted, which is that gxy equals xyg. One condition left to check, so let's check the inverse condition. So here, to check the inverse condition, we're going to start with any element in the center, and we want to show that its inverse also belongs in the center. And so what does it mean for the inverse to belong in the center? Well, again, what is our definition to belong in the center? It means for any element g, we can multiply on the right or the left, and we'll get the same answer back. So this is what we're trying to prove. So once again, we're going to start with the left-hand side, and we're going to try and manipulate it. But we'll have to be a little more clever this time around. So this first equation, we're allowed to multiply by the identity. We talked about that at the beginning of the video. So we'll multiply by the identity on the right, and then our secret trick here is that this itself is the identity. We know that x has an inverse because every element in a group has an inverse in the group. That's one of our properties of the group. So we can do this because of the inverse property. And then you can see we use associativity again. We use the definition of the fact that x is in the group to switch gx into xg. And then the key here being once we get x and x inverse together again, it becomes the identity. And sure enough, we get what we're looking for, which is that gx inverse on the right-hand side there. And that means we've shown the conditions for our lemma, and we conclude that the center of a group is always a subgroup of the group, no matter what group you start with. Thanks for watching this video. I hope you enjoyed it. Make sure to subscribe so you don't miss out on future videos. And if you have a question about this problem, or if you'd like to request a solution to a different problem you're working on, let me know in a comment below.